We can use the Clapeyron equation to develop equations for all the pressures and temperatures at which two given phases coexist. This is exactly the kind of information that is contained in a phase diagram, so we can use these equations to construct a phase diagram for a substance. Let's look at how the coexistence temperature for a liquid and a solid depends on pressure. Recall that the Clapeyron equation tells us that the derivative of pressure with respect to temperature for a phase transition is equal to the enthalpy per mole, change in enthalpy per mole for that phase transition, divided by the temperature at which that phase transition occurs, and the change in volume per mole for that phase transition. If we apply this equation to a liquid-solid equilibrium, so if we have a substance in the solid phase in equilibrium with its liquid phase, then the delta H for the phase change that we're talking about is delta H for melting, or delta H of fusion. And in this case, we're looking at delta V for the phase change as the molar volume of the liquid minus the molar volume of the solid. We will now make the argument that the molar volume of the liquid and the molar volume of the solid do not change much with pressure and temperature. Therefore, we can approximate this change in volume as approximately constant. Thus, when we separate variables and integrate, we have dP is equal to delta H of fusion per mole divided by the delta V of fusion per mole times dT over the melting point temperature. When we integrate this equation, we're going to integrate again from the normal pressure of 1 bar to any other pressure, and we integrate delta H of fusion divided by delta V of fusion dt over T from the normal melting point to any other melting point for the solid. The delta H and delta V of fusion are going to be approximated as constant, and so we bring those out of the integral, and we have P minus normal pressure of 1 bar is equal to delta H of fusion per mole divided by delta V of fusion per mole, natural log of the melting point divided by the normal melting point for the substance. And this then describes the coexistence curve for a liquid and a solid, or indeed any two condensed phases.